Okay, so this video is going to cover Newton's law of cooling, and once again, I do not have my calculator, so I'm going to have to rely on the numbers from the book, so just hang with me. So this is the formula for Newton's law of cooling. All right, U of T is the temperature that your object has cooled down to after time t. Now, capital T is the constant temperature of the surrounding medium. So this is pretty much air temperature, or we call it room temperature. Now, as you look in your textbook, it tells you that it's the constant temperature of the surrounding medium. So you can understand room temperature. We deal with that often. Now, U subscript 0, that is going to be the initial temperature of the heated object. And so go ahead and write all this down. K, because it is a cooling or a drop, is going to be negative. Okay, and T, which is your time, can be measured in any amount. Not like money, which needs to be in years. You can do any amount here. So, with that being said, let's look at our word problem. It says an object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. So on part A, it says if the temperature of the object is 80 degrees Celsius after 5 minutes, when will the temperature be 50 degrees? So looking at Newton's law of cooling, we need to solve for T, don't we? But nowhere in that problem does it tell me what K is. So before you can solve for T, you've got to solve for K, just like in the carbon-14 dating example. So look at what you've got in our first paragraph. An object is heated to 100 degrees Celsius. Okay, 100 degrees Celsius is going to be your U of 0. Okay, and is allowed to cool in a room whose air temperature is 30 degrees Celsius. So a room with an air temperature of 30 degrees Celsius, that's our big T. Okay, so now that I have this, what I'm going to do is I'm going to plug in what I do know into my formula. So that's going to be capital T plus U of 0 minus capital T e to the kt. So let's simplify what we have here. 100 minus 30 is 70. So this is my basic function, okay? My generic function. Notice I don't have a k or a t. So the first thing I'm going to solve for after I write my generic function is I'm going to solve for k. In order to solve for K, I'm going to use part A. The temperature of the object is 80 degrees Celsius after 5 minutes. So they gave us a ratio here. So it's 80 degrees Celsius after 5 minutes. Let's plug that into our formula that we've come up with, this generic one, so that we can solve for K. And once we got K, we can answer the question. So 80 degrees is what the object has cooled down to. That's going to be our U of T. So 80 degrees equals, well, we got 30 plus 70 e to the k. Now, it took 5 minutes for this object to go from 100 degrees to 80 degrees. So that means my T is 5. So let's get E by itself. Let's divide by 70. So we get 5/7 is equal to e to the k, 5. Now we'll take the natural log of 5/7 on the natural log of e to the k, 5. Remember, log base e of e, we'll drop down and make that. We'll put 5k, and then we'll have the natural log of 5/7. So we're going to divide both sides by 5. Now remember, K should be a negative value. So when you plug in the natural log of 5/7 divided by 5, you should get a negative number. Now this decimal is not going to be near as bad as the one that we had in the carbon-14 dating example. So I'm only going to go out 4 decimal places on this one. So now I know K. So let's go back to our little generic formula right here. U of T is equal to 30 plus 70 e to the K T. And now we'll answer the question. The question is, when will the temperature be 50 degrees? So when will this object cool down to 50 degrees? So we're going to look for T this time. Subtract 30 from both sides. Divide by 70. And we'll get 2/7 is equal to e to the negative 0.0673 t. Now we're going to take the natural log of both sides. Natural log is log base e of e, which will cancel everything out, and you'll have the natural log of 2/7 is equal to negative 0.0673 t. Now let's divide both sides by our decimal. Now this being a time, it's got to be positive, y'all. Okay, so when you plug it into your calculator, the natural log of 2/7 over this negative decimal, okay, you are going to get approximately 18.6 minutes. Okay, and that is Newton's law of cooling.